So my name is Knute Lingaard. I'm a Senior Director at MIPS Tech on the Performance Modeling Architecture team. I'm also the co-chair of the RISC-V Performance Modeling SIG, also known as the Olympia Performance Model. I'm also the lead maintainer of the Sparta Modeling Framework. I'm not going to get into that today, but it is the framework that Olympia is based upon. So moving forward. The agenda today, just going to go talk about the value of performance modeling. Let's just start off with that specifically. What value does performance modeling have in any kind of CPU development? I'm going to go a little bit overview of the Olympia Performance Model, give an idea of what it is so we have a topic of conversation. And then I'm going to give an example of essentially how we can use Olympia to, for example, look at a specific analysis flow, how you would run it, and so command line options and examples and so forth. And then I'm going to show you a debug of a real world use case that I had where I actually had to fix a performance issue in the performance model itself. Okay, so the value of performance modeling. So the performance modeling can be broken up into three specific use cases. There are probably more, but these are the ones that my team and so forth in multiple places have specifically focused on. The first one is microarchitectural development. You have usually two designs. So if you come into a company, you have either a current design that essentially has some issues and performance issues, and you have some very basic rudimentary ways of developing or debugging it, so to speak, on performance. And you also have new designs where you're going to explore brand new microarchitectural ideas. So you have an architecture team, development team that wants to explore and look at brand new ideas. The quickest way to actually look at both of those and look and deep dive into each one of those is with a performance model. Tons of introspection, tons of ideas that you can gather and bounce back and forth. That's the first use case. When you usually have that performance model up and running and it represents either a current microarchitecture or a new microarchitecture, one of the benefits is naturally you have to have software. So it's always a two-handed approach. You have hardware, which is going to essentially run software as best as it can, but you want to be able to tune that software to make sure it works well on that hardware. If you have a proper performance model, it can help the software tuning aspects to illustrate, and you can even flag specific issues the software is doing. So you can use software tuning. You can use that model specifically for software tuning. And then the third final kind of usefulness is essentially co-simulation. You can integrate essentially a model like this using, for example, System C, TLM type of interfaces into an existing microarchitectural design. Maybe you've already got SoC models, and you can integrate it in, and you can help drive essentially in C transactions that are going all in simulation environments or even in, for example, Verilator type of operations or Verilog type of operations. Okay? The last bit, of course, is you can also, with co-simulations, correlate it against the design. So that's one thing is you want to be able to integrate it in and then have the actual RTL design lockstep with the actual performance model, and they can compare against each other. You can flag initial performance issues even in the hardware as early as possible. Okay, Olympia. So now you have a general concept of essentially what is a performance model, what it can be used for. Olympia is a representation of a CPU performance model. So what Olympia is, it is a model that's written in C++. It was developed, we developed it with my chair, Roop Chakraborty, developed it in the RISC-V community as well as an example of an out-of-order CPU performance model. So it's a starting point of a RISC-V CPU performance model. It doesn't actually represent any true microarchitectural design that's currently out there in the RISC-V community. Though we've had discussions in the background, should we model something like Boom and so forth, and we've been talking about that in the past, but it's also a relatively new model. It's only been on the scene for a couple of years. It enables the community to share ideas, performance exploration ideas, but it's also what we're using right now as a researching tool to get new people involved in performance architecture modeling. We have interns that come in, we have people that are in the industry who help contribute to the model to be able to extend it and be able to convert and change it, find bugs and so forth, to be able to get it to a much more usable performance model, whether it be a starting point for current designs or a starting point for brand new designs that you're looking in CPU design and model. The main purpose of it is to be extremely, and one of the requirements when you're developing and so forth on this performance model, it has to be highly configurable, very modular. The idea is that you want to be able to swap things out, change different ideas, go different directions. You want all of that to be able to work well, and you want to be able to do it at runtime, not compile time. And then, like I said, it's also based on the Sparta Modeling Framework, which is an open source framework that is specifically focused. All it does is just help with performance and functional modeling development. If you have models that are based on the Sparta Modeling Framework, they can interact with each other. If you have models based on the Sparta Modeling Framework or a System C or TLM type of interface, Sparta will also support that. So they'll all be able to integrate well together. Okay. This is our basic Olympia CPU pipeline that we have currently modeled. We have a very simplistic fetch front end with a very simplistic branch prediction API, so you can swap in different branch predictors. That's under development. Simple decode, which has a fantastic framework that was developed that allows us to be able to try different decode fusions and capabilities. That's also a part of it. We have a simple rename, dispatch, and of course dispatching policies to different issue to different issue queues. Arithmetic execution units, retire. We have a load store unit, load store pipelining. We also have an L2 cache and basic memory latency with just brain dead memory latencies to represent your DRAM accesses. So that type of model, that's the general pipeline. That is what you get when you get essentially download Olympia. And the configurability on it is pretty straightforward. It supports numerous ISA extensions. We're adding more. It supports both RV32 and RV64. It supports vector. You can do things like you can explore machine widths between any block. You don't have to say it's 4 wide all the way across. You can say it's 4 wide, 6 wide, 8 wide. You can do something crazy. You can do all kinds of things like that. You can configure typical stuff, and you see in most performance models, configurability representing your queues, buffers, arrays, pipelines, and the different sizing on that. But they are specifically using the Sparta-based ones, which contain specific information. For example, they contain like utilizations and things like that, so you can get an idea. Maybe you can use that for power analysis, and there are companies that have done that. There are branch prediction algorithms. There's a branch prediction API that's being added onto it. Decode fusion pairings, I mentioned that. There's a fantastic framework that's being developed for that. Rename PRF sizing, dispatching algorithms, how you want to distribute essentially your topologies for issue queue and execution pipelines, one issue queue per one pipeline, one issue queue to multiple pipelines, whatever you'd like to try. Load store pipeline depths. You can actually program the load store unit to say how deep you want the pipeline to be, where you want it to have specific types of transactions to occur. And then data cache, L2 cache sizes, all these things are configurable, and we're adding more configurations as time goes on. Okay, so now you have a concept of essentially what Olympia is. A C++ model. It represents kind of a rudimentary CPU pipeline design. And then we have the use cases and the development and so forth. So how would you actually use this performance model if you were taking it for yourself? It is, as far as its input, it requires right now today, although we're going to extend it, it's a trace-driven simulator. So what happens is you take an application or workload, you use a functional model. For example, we're currently using the Dramaggio functional model, but using the STF library, which is part of the Sparta modeling framework, where the Sparta modeling framework resides in the repository in GitHub. Right next to it is an STF library, COSIM API, an API for it, trace reader writer. You can instrument a functional model with the STF library. Documentation is there, and then you should be able to generate any trace that you want. It's specifically an instruction stream. So it's just as the program is running on the functional model, every instruction is essentially recorded in this binary format. You can extend it with all kinds of records, exception handling information like that, register source destination information. It can be a full-blown trace that represents the program execution. Keep that in mind because there's a lot of powerful things you can do with just the trace, and I'll show you how you can do that. The output from Olympia, after it's consumed and run that trace that was generated from a functional model that's static on disk, you take that trace and you run it through Olympia. You can program Olympia, ask it to generate tons of information. It can generate reports, different types of formats, text, HTML, JSON, CSV, Python dictionaries, whatever you want as far as your backend tools for slurping up data. You can take snapshots at different times using triggers. So it's like, I'm running a trace, but I really don't care about all this stuff up front. But as soon as I hit this instruction or this behavior or this type of, wherever it is, you can define whatever trigger you want. That's when I want you to start actually generating and consider that time zero for report generation. So you can take snapshots. You can do time series reports every cycle, every 1,000 cycles, 100 cycles, whatever you want to see. Give me a time series of all these or a specific subset of statistics and collections that you want so I can graph them. And then you can do correlations or causations. You can look for how do statistics relate to each other. You can generate pipeline crawls, and I'll show a quick little example of what that looks like. And it's basically just a pretty, we call them the rainbow charts. So they're all different colors of essentially showing instructions flowing through the pipeline. You can generate performance events. These are very powerful where you can simply say, I want points of interest in the simulator that I want to see. When do I fetch? When do I dispatch? When do I decode? So forth. When do I retire? Those are really powerful because it's just a simple text log file that you can actually compare against RTL development. If you instrument the RTL, or like in the previous presentation that was here talking about trace, you can actually generate a trace, and then you can generate a trace using performance events, and you can compare the two. Is the performance simulator representing what the RTL is doing? So you can do a correlation. And then last is logging. Everybody needs logging to be able to what the heck is going on when you're debugging the simulator. The logging, most time, in most simulations I've ever used, is just turn it on and wait until you fill up disk. In this case, you can actually specify triggers where you want logging. You can specify data-specific points in the simulator you want it to log. You can specify the types of logs you want to look for. You can narrow down to a specific subset of information that you're looking for. So it's very, very powerful. All of that comes for free with the Sparta modeling framework that Olympia is built on top of. Okay, so here's how a typical analysis flow works. So you start off with your workload up here, your typical binary compiled generation, and you run it through a functional model that's been instrumented with the STF library. The STF, and when it generates, it'll generate an STF trace. This is what's statically on disk that represents that instruction flow. So as the instructions are flowing, or essentially it's saved on disk, you can actually do lots of things with that trace. First thing you can do is you can use a plethora of STF tools that we do supply as well. It's part of the same GitHub repository where STF resides. You can do things such as you can take this trace and give me an idea of the instruction flow. Give me some instruction count profiles. Look at instruction mixes. Show me load store data. Show me branch prediction data. Anything that's static to that trace that you don't need to or care about performance data. You can actually do some interesting things just doing this to give you kind of an idea. Maybe you're looking for fusion capabilities. Maybe you're looking for ways where you can actually see what is the distance between load to use in most of the things, and you can even feed that immediately back to a compiler team, for example, and then regenerate the trace and see if it changes. You didn't run a performance model on that. You just looked at the program flow. But that trace is then actually sent now to Olympia. And you run Olympia on that, and it'll generate, as I said earlier, you can generate a report, you can generate a pipe out, which is this rainbow chart here. You can generate performance events and so forth. The reports for plotting, you can generate a CSV file. We have two tools. Argos is the name of the tool that generates the rainbow chart. And then PlotTS is another tool that comes essentially with Olympia, but it allows you to generate, and it's very rudimentary. It's like 100, not even that, it's like 10 lines of Python, so you can look at that. But you can start building. The idea is that these are all the basis for tools that you can build on top of. Okay, so let's run a workload. So by default, out of the box, just for grins, Olympia has 3 configurations that we supply to give an example of how you would actually configure it. So we have a small core, a medium core, and a big core. And each configuration just does something kind of rough, relatively brain dead, where it just simply says, let's widen the machine, let's add more execution pipes, let's look at more things like that. So here's an example of going from a small core to a medium core. So we went from a 2-wide machine to a 3-wide machine, and we've increased going from 4 pipelines to 7, just for grins. Let's see what that works. Each one of these pipelines, of course, represents what it can functionally do, each one of those lines. This is only a tiny subset of the differences between those two. There's other things that you can look at as well if you wanted to diff the two, small versus medium core. And if you run this essentially on Drystone, you can take, for example, the small core, which Olympia by default, it says, I've been told when it was built a long time ago, I will look for the small architecture and I'll run that. So it's as simple as just simply saying, Olympia, run this Drystone trace. Drystone is something we provide with the simulator so you can play with it and get an idea of how it works. So if I remember correctly, this Drystone binary was generated by the Dramaggio functional model some time ago. The command line here, report all, says report all your statistics and counters without any filtering to standard out, which is, of course, 1. Standard error is 2. But if you go beyond that and provide anything that's not 1 or 2, it assumes it's a file, and it'll save it to file. And then just grab for the IPC. Now, in this example here, I ran Drystone on a small core, but it's showing an IPC of 0.38, right? Now, Drystone you really talk about in DMIPS. MIPS. That's all you talk about. So the idea, but here I have a report that you could do a dry stone MIPS type of analysis, and there is a report that would provide you a dry stone MIPS number based on the stats and counts, but the IPC in general should it relates to that. So what's interesting, what's going on? Why is it only at essentially 0.38? So let's go to the next core. Let's try the medium core, see if that gets any better. The medium core, if you remember correctly, it adds a whole bunch more pipelines, it widens the machine. We should see a much greater IPC growth. So if I rerun this dry stone trace on essentially the medium core and I add more resources with a wider machine, it's the same stuff, but this time I say architecture is medium core. The IPC improves, but only by 8%. That's terrible. That's not very good. So what's going on? Dry stone, as we know, is an inter-J-based workload. It mostly hits in the data cache after warm-up. It should almost always hit in the data cache. So the medium core added two additional integer pipelines. That probably helped. So some performance uplift was expected, but shouldn't there be more? That's the question. And so, granted, I'm giving you a very simplistic example of how to do this, but when you get into really high-performance CPU out-of-order designs and so forth, this is the type of deep dive that you would actually do on a much larger level. So the same application or example I'm showing here will actually apply. So we rerun the simulation, but this time I want to generate reports instead of the standard out, which was 1. I'm going to actually report them specifically to their own text files. So rerun with the small core to small run, rerun with the medium core to medium run, and then basically diff the two. Just diff them. Now I'll give a hint. Most of the time when I'm doing performance analysis and so forth, the first thing I look at is dispatch. Because dispatch is your last point typically in out of order, in an in order to out of order type of environment. So dispatch, if it can't make forward progress, where it can't essentially send out instructions everywhere, that's an indication you've got a performance blockage somewhere. So I look here and I see that stall BR busy. These BR is a branch unit. And I noticed that the dispatch stalls on branch went from 1 to 30,000. That's a lot. That's not good. And then we also noticed that essentially stall int busy, well, it dropped quite significantly. It went from 570,000 to 50,000. Well, that's good. So that was expected. Remember, the medium core added more integer pipelines. So then the next part is, well, let's look at LSU busy. Well, it got worse, but it's roughly within the same kind of number of counts that are bad. And also the medium core added another multiply unit. And of course, dry stone's got a couple of multiplies in it, and that went to 0. That's good. That means that multiply is being satisfied. So I guess what we did is we gained some performance just by simply adding that integer and multiply. But at the same time, the fact that dispatch not stalled, in other words, we want all of these counts here to move to this count here. I want dispatch not to be stalled. It needs to push instructions through. And it went down, which is not good. You want this number to go up. You want these numbers to move to here. Okay. So let's go a little deeper into this. Let's look at the dispatch, essentially point where it said BR was busy. We're very high. That's not good. So let's try an experiment, just for fun. Let's add a second branch unit. Now, when you add a second branch unit, that adds all kinds of complexity to the machine. Specifically if you're trying to redirect fetch on branch mispredictions. But you look at this here, what I did is I said, all right, let's copy the medium core, which is the standard one that comes with Olympia. We'll copy it to another microarchitecture called second BR, medium core second BR. And then what I did here is on exe2, I added another branch unit. That's all I did. And now we run Olympia again on the new architecture called medium core second BR, same trace, and report to a new report file and compare the two. Hey, look at that. My branch busy went to 0 and everything moved over to integer. So we just shifted the problem to something else. And what we all like to say is that's whack-a-mole. So what we're doing is one mole pops up in this video game. If you ever played it, you hit it, another one pops up. So all you're doing is just constantly chasing essentially these moles and trying to get them down. The sad part about it is while busy dropped to 0, the bottleneck definitely moved probably somewhere else to load store unit, obviously to the integer one because it had problems. And the IPC didn't change. It's the same IPC between medium core and medium core with a second BR. It did not change. So obviously everyone's probably thinking, or some folks are thinking, the load store unit is probably our culprit. Now remember, dry stone should stick around, should be able to handle and hit the branch, the L1 cache. So let's take a look at the load store stats. DL1 cache hits very high, misses very low. Okay, well, that's good. That means that the load store unit still it seems to be hitting in the cache. That's good, but it doesn't seem to be resolving its own loads and stores that it has. It should be doing much better than that, because dispatch is saying, I can't make forward progress. Load store unit's constantly stopping me. So let's look at the load store pipeline. Optimally, if you think about it, if you just had a workload that had just had a whole bunch of loads, all to the same address, that should get at least a 1.0 IPC. Just flows right through if it hits in the data cache and it hits in the TLB. So let's write a small test. Remember, Olympia can take two types of tests. It can take a trace, and I guess I didn't mention it also can take a JSON file. JSON files, you can just hand write them, and then you can run that test. Very handy for correlation, very handy for what ifs. And so let's write a small JSON test. The JSON test, I just have a simple load that essentially address offset off of 4, write to 5, and with a V-adder essentially aligned, that's critical, aligned V-adder essentially to 0. So I have this, here's one load, here's the second load, and I just copy pasted this 98 more times. So I have 100 loads in a row. And then I ran that on Olympia. Now Olympia, you can tell it, go ahead and just simply say TLBs always hit. So if I go to the MMU is like, I got this, it's no problem. And then same thing with the L1 cache, it's an always hit. These are infinite caches, infinite TLBs. You know, very easy to build in hardware, but they don't. So we went ahead and just tried to go ahead and just get that out of the way so it's not noisy. And then run this, essentially this JSON file, which is also supplied in Olympia if you play with it. It's called many loads. Generate a performance events, essentially a retire performance events, and then generate a new report and take a look at it. If I look at that report and I grep for IPC, it's half of what I expected. That's not good. So that's obviously something going on in the load store unit that needs investigation. So now you got to start taking apart the load store unit. And we started taking apart the load store unit. Remember I gave that P events where you simply look at the performance events for retire. I see that there are random bubbles between the retirements of load. I've got a load that's retiring at 15, 16, 17, 18, and then all of a sudden we have 4 cycles of doing nothing. And then 23, 24, 25, 26, 4 cycles of doing nothing. So obviously we have a bubble that's going on. If I bring this up in the pipe view Argos, you can see, there they are. There's the 4 holes. So something's wrong. The next question you ask yourself, is this a bug in the model or the design? And I think that's obvious, it's a bug in the model. Why is the model doing this? And I'll give you a hint, essentially it was a bug in the model, and I know exactly what it was, and believe it or not, I opened a PR on this last week to fix this in the performance model. The issue is and this is where it gets tricky. Each one of these instructions, B, C, D, E, F, and so forth, all these numbers, you can see it repeats B, C, D, E, F. Every 4 cycles or so forth, it reissues those same those loads back down the pipe again. And that's what's happening up here in the retirement log as well. What's happening is that when this instruction, when one of the loads gets to the essentially cache read stage, the way the Olympia models the load store unit and models the data cache is it represents pipelines. So it sends the load down the load store pipeline, which will send a cache request across. And then in the next cycle, it expects that cache request to come back to say it was a hit or miss, and so it can continue on and do data forwarding onto the middle machine. It turns out there was a bug in the model where the cache was sending that signal 1 cycle late every single time. And so what happened was it would come in 1 cycle late, the load would go into the load store unit, it would eventually get to the data cache read stage, see that it was a data cache miss, throws it back into the replay queue. And then it comes back down again. When it comes back down again, it was told it was a hit, because right after that, the cache said, well, actually, you were a hit. Sorry, I was late. And when it came back through, it says, oh, you were a hit. And then it would cycle it through. So there was actually 2 bugs. One is an assertion was missed. We should have caught that. If it's already past essentially a data cache read and you're setting it a hit, that's not good. So that's a bug right there. The second one, of course, is that we have this timing issue where the data cache was not sending a response back to the load store pipe fast enough. This is an interesting thing in Sparta Modeling Framework, and one of the things that we really like about it, Sparta Modeling Framework, you can order events. Each one of those things that I was talking about is an event that goes across. And the framework organizes the events based on how you say things are supposed to happen in time. So the load store unit comes on and it says, I'm expecting and requesting essentially a data cache read. Data cache read says I'll put an event in, and when I have my time to actually do my data cache read and I put a response, that response has to come before the load store unit asks for it. And that was missing, and they swapped order. So all I did was just add a small order saying, this event has to come before this one. As soon as I swapped the order, these pipelines, this hole disappeared, and I got 1.0 IPC right off the bat by making one small fix to the simulator. So those kind of things are pretty powerful. If we had essentially hardware, let's pretend this was a hardware issue, which is most likely never going to happen, but let's pretend that this is a hardware issue. This could go unnoticed. And so the idea is that if you had essentially this retirement P event concept, and maybe you have a trace from the RTL, or you instrumented the RTL with the exact same concepts, you can compare the two. And if the RTL is doing the right thing, then the model would obviously be flagged immediately. That's a problem. And there's your load store. That's the issue. It's a load store issue. But let's pretend it's the other way around. Maybe Olympia actually got this right and was doing 1.0 IPC, and the hardware had a delay. Every fourth or fifth cycle, or every fourth or fifth load, for some reason it had a hiccup, and it always added a bubble. You can catch that immediately. Those are lost cycles. If you're doing hundreds of billions of cycles, that adds up very quickly. So looking at these little individual things like this makes a huge difference. So anyway, that was an example of how I use essentially Olympia, or how we use it in the industry, how we take it. The investigation will continue on things like this. That was a very simplistic view of a real CPU issue in CPU development. But what I want to stress more than anything else is Olympia, if you take it out of the box and you look at it and you say, this doesn't represent something that we would build, of course not. That's not what it's for. What it's for is to give you a starting point, a template to actually augment it, change it, getting all of the things out of the way, such as application runs, trace generation, essentially your basic topology. You already have most of your statistic encounters are already in place. Now you can just use them. And you can model it to represent your current designs, your next generation designs. You can change it the way you want to represent your next CPU development for RISC-V. So using that Olympia with this lockstep and CPU design, you can make sure that both the RTL that you're trying to build represents what you are telling your customers, for example, out of the performance model. This is what we're planning on doing. This is what we're planning on making. You can keep the RTL in lockstep with what you're doing. So thank you. Appreciate it. Go to questions.